Hello and welcome to this final lecture in the course on pattern recognition. We've been last class we've been looking at classifier ensembles, that is how can we combine many different classifiers we learned for the same pattern recognition problem, so that we can improve the accuracy. We briefly looked at an algorithm called AdaBoost today, one of the best classifier ensemble algorithms. Today's class will complete our discussion on AdaBoost. We will look at AdaBoost also from a risk minimization point of view. So, to continue, we said boosting is a general approach for designing classifier ensembles, right. So, we looked at a simple intuitively designed boosting algorithm of learning 3 classifiers, just to get an idea what boosting is about. And then in general there are many techniques of boosting, and AdaBoost is a very popular method of designing such ensembles, because it allows you to design an ensemble of almost any size, and in practice it works quite well. So, let us go back to the algorithm. We have discussed it last class, but we will look at it again. So, the idea of AdaBoost is that I assign weights to each of the examples given. I got n examples x I y I. So, each example I assign a weight changes from iteration to iteration. At any given time the weights are always kept normalized. So, at each iteration I use the weights as a probability distribution and sample from the examples. That is, the example x I y I, I keep taking n random samples from this example set. So, at each time the sample is independently chosen, and the fact that an x I y I, the probability of an x I y I coming into my training set is given by w I, the weight at that time, w I of m if m with iteration. So, essentially the examples with higher weights are more likely to come, and of course, this is because I am using w I as a probability distribution and sampling IID. It is like sampling from the example set with replacement. So, multiple times I draw an example, I might get the same example. So, this is particularly true if a particular example has very high weight, it may be represented more than once in the training set, but without counting such not bothering about such repetitions, I have size n for my training set. Each training set is of size n, and of course, some of the examples may be repeated because they are sampled with w. So, the algorithm starts by initializing the weights to 1 by n. That means, initially each example is as likely to be chosen as any other example, because you have no preference on examples. Then I keep learning classifiers, capital M is the total number of classifiers in my ensemble. So, that is my iteration count. So, at the mth iteration I am learning the mth classifier. So, what do? I generate a training set by sampling with these weights. Then you learn a classifier HM using this training set. We have not said anything about how you learn this classifier. It can be any method. It can be a neural network, it can be SVM, it can be linear classifier, it can even be decision tree. We haven't considered decision trees except in the first introductory class I talked about. We won't say what the classifier is. Also, as I said, on different iterations you may use different classifiers. All that is of that does not affect the algorithm. So, whatever is our preferred way of learning the base classifier, each of the HMs are called base classifiers. We learn it, and then we calculate the error. Jm is the weighted error. See, indicator of y not equal hm xi, it simply means on this example I made an error, right, and the error is weighed by the weight of that example at this time. Mind you, this is not necessarily the training set, because the training set is randomly chosen, but this is on all the examples I have x I y I, right. For each example is classified by the newly learned classifier, and wherever I misclassify, my actual error is weighed by the weight of that classifier. So, I want to minimize this weighted sum. In a sense, I can say I want to learn a classifier HM which minimizes this weighted error. Okay. We assume that each of the classifiers we learn is such that the error is less than 0.5. In practice, all it means is if I had a classifier whose error is greater than 0.5, I throw it away and learn again. Then set alpha m is ln 1 minus j m by j m, because we assumed j m is less than 0.5, 1 minus j m is greater than j m, and hence alpha m is always positive. Then for the next iteration, I learn new weights. So essentially, I want to keep weights normalized. So the unnormalized ones, whatever the old weight, I increase the weight if I misclassify this example at this stage. If y I is not equal to h m x I, then I multiply w m by exponential alpha m, because alpha m is positive, this is greater than 1, or exponential alpha m is greater than 1. So, increase the weight, and then I finally normalize all the weights. Okay. And my final classifier, after learning all the h m's, my final classifier is simply summation m is equal to 1 to m alpha m h m x, where these alpha m's are what we calculated, which is ln 1 minus j m by j m, where j m is the weighted error of the nth classifier. So, alpha m is some kind of a weight for the accuracy of h m. So, I take this sum and its sign is what I am using as h x. Okay. So, this is the algorithm that we considered last time. The algorithm allows one to learn a set of classifiers for a problem. M is a parameter, as we said, we can learn arbitrary number of classifiers. So, we can learn ensemble with any number of classifiers in principle. After learning each classifier, we update the weights. The whole idea of the weights is weight update is such, as I just mentioned, is that if h m x I not equal to y I, then w I m plus 1 is greater than w I m, right. If y I is not equal to h m x I, then this will be exponential alpha m, this factor, and alpha m is greater than 0, alpha m is positive. So, this is greater than 1. Okay. So, w I prime m plus 1 is greater than w I m, and hence after normalization also it will remain. On the other hand, if y I is equal to h m x I, then this factor is 1. So, w I prime m is w m. So, essentially in w I prime, I am increasing weights of all examples which are misclassified, leaving others where they are, and then renormalizing, which means if I have misclassified an example, then its weight for the next iteration increases. Okay. So, we ensure higher weight is given to previously misclassified examples, essentially that is the whole idea of generating successive training sets. Okay. However, we do not want only misclassified examples, we already looked at it when we consider general boosting. That does not give me enough variation in the training set, right. So, it is not that we can just arbitrarily increase the weightage or sample only from the misclassified examples for the next iteration. We also want to maintain proper variability in the successive training sets that are generated. As you have seen, we want a good balance between misclassified examples and properly classified examples, right. So, this is also achieved by the weight update scheme of AdaBoost, right. This is what we saw last class. As a matter of fact, last class we proved that the weight update is such that if I sum all the weights over all I such that x I y I is misclassified by h m, that sum is equal to sum of all weights over I such that h m x I is equal to y I. So, because total weights is 1 and these two sums are same, each is half. What does that mean? The weight update is such that at the next iteration, half the total weight is for patterns misclassified by the current classifier and half the total weight is for patterns correctly classified by the current classifier. Right. This is automatically achieved by my weight update equations. My weight update equations form is such that this is achieved. Right. We proved it last class that this happens to be so. Now, this is a very interesting thing about the algorithm. The algorithm, so this way the algorithm automatically can generate as many training sets as you want of required variability. We do not have to worry about it. The weight update equations are such that they maintain this. Okay. This gives sufficient level of variability in successive training sets. Okay. A word about the final classifier. What is the final classifier of this ensemble? After learning all h m's, Alpha m is, as we see in ln 1 minus j m by j m, where j m is the weighted error. So, lower j m, higher is alpha m. Okay. So, I take alpha m h m x and take summation and take its sign as my final classifier. Please remember, all this algorithm, everything we are considering only for the 2 class case, where the class labels are +1 and -1. So, when I take the sign function, if this sum is positive, then the sign is +1, otherwise it is -1. Essentially, you can easily see that because each h m itself is a classifier, we assume that h m x is either +1 or -1 for every x. So, because each of the +1s, if all alpha m's are constant, so alpha m is constant and positive, then it can come out of the sign function. Then, if the sum has more +1s, finally the sign will be +1. The sum has more -1s, finally the sign will be -1. So, essentially it would be a simple majority voting if I did not have alpha m. Right. So, if I had alpha m, what it means is that it is a weighted majority vote. If I did not have alpha m, each classifier's vote has the same weightage. So, I am asking how many classifiers say +1, how many classifiers say -1, and I am taking the majority. Now, I am not doing that, because each vote has a weight. I am summing up the weights of all the +1 classifiers, summing up all the weights of -1 classifiers. I am asking which is better. The weight is alpha m. Weight depends on how good that classifier has been performing, right. The weight is based on the accuracy of that classifier. So, this is a very interesting way to combine, and once again a very general purpose way to combine classifiers, what is called a weighted majority vote. This is also a very interesting feature of this AdaBoost algorithm. Okay. The interesting thing about the algorithm is it can generate a classifier ensemble with any number of component classifiers. So, there are many applications, face recognition, image classification, many areas. People have used this, and there are in many applications people use 100, 200 classifier ensembles. Okay. So, the algorithm can generate classifier ensembles with any number of component classifiers. As you can see, our weight update is such that successively I can keep generating size n training sets which have the right properties by updating weights and sampling with those weights, and hence the algorithm is a very general purpose algorithm with lot of power. Second thing nice about the algorithm is I do not worry about it's not as if it is applicable only for one type of component classifiers. You can put decision trees, you can put neural networks, you can put things learned through linear least squares, you can learn through what have you. Okay. There is no restriction on the type of the component classifiers that you can use. All that we are asking for each classifier is that j m less than 0.5. I said in practice I keep doing it, and if any time my algorithm returns a classifier with j m greater than 0.5, I throw it away and learn again. But in general what we are asking is that each of our classifiers should at least have j m less than 0.5. So, in this weighted sense they should be better than pure chance. Okay. The idea is that if the weight is high, that particular example will be multiply represented in your training set. So, even if I am counting training set error, if I misclassify that one example, it will actually be counted as 3 or 4 training set examples are misclassified depending on the weight, right. So, in that sense essentially because the training set itself comes with the weighted error being less than 0.5 is roughly same as saying that I will get the right classification more than 50% of the time. So, basically what I am asking is I can't have very bad classifiers. Classifiers should be at least good enough to be better than pure chance guessing. Just that much. These are very weak classifiers. I am not asking much. I am not saying their accuracy should be very high. All I am saying is their accuracy should be just a little better than pure chance. So, that is the strength of this kind of boosting techniques, right. Such classifiers are called weak classifiers because they can only achieve a little better than pure chance guessing, but that is good enough. If you give me many such weak classifiers, while nobody alone can get very good accuracy, if you give me 100 or 200 of them, combining them properly, I can get very high accuracy. So, the strength of AdaBoost is that it can combine many weak classifiers into coming up with a very good high accuracy classifier. Okay. as long as each component classifier has an error rate better than 0.5, the ensemble in practice does very well. A matter of fact, with just a little algebra, we can show, even though in this class we are not showing it, but it is not very difficult to show that the training error of the ensemble classifier decreases exponentially with increasing number of classifiers in the ensemble. As long as we maintain this weighted error less than 0.5 for each component classifier, one can show that the training error of the ensemble decreases exponentially fast with increasing number of classifiers in the ensemble. That is a very, very nice property to have. Of course, we know that low training error does not necessarily mean low test error. We can be doing overfitting. The reason why overfitting may not be occurring in AdaBoost is twofold. Firstly, we know it does not, in the sense in practice on many interesting applications, many benchmark problems, it does very well. One possibility is that because each component classifier we ask for need to be only just a little better than pure chance guessing, we can work with low complexity classifiers. We do not have to take very high complexity classifiers. Because of that, right, essentially low training error could mean low test error, and because ensemble gives me sufficiently low training error, it also gives me low test error. Roughly, one way of looking at it is that ensemble allows me to get higher accuracy. I do not have to go to very complex classifier structures. I can use simple classifiers, let us say just linear classifiers, but I use many of them. That is the strength of boosting. Of course, the particular AdaBoost algorithm we presented is such that we assume that each HM is a classifier, that is a binary valued output. HM of x takes only values +1 and -1. So, this AdaBoost is called a discrete AdaBoost, because each HM takes on only discrete values, the class labels. Of course, the AdaBoost algorithm itself can be extended to other cases where HM returns a continuous value, say for regression problems. Also for classification problems where HM could be a neural network. So, HMX is a continuous value, or say logistic regression. So, I can use any such classifiers also, and the algorithm is slightly different, but still similar conclusions hold. So, one can also extend the algorithm that we presented to the case of HM that return a continuous value rather than a discrete class label as well. Okay. So, in this sense, AdaBoost is possibly one of the best off the shelf classifiers that are available today. Okay. Just like kernel based classifiers are good, and as I said, they should be the first choice whenever you are looking at a classification problem. Similarly, a boosting AdaBoost is a very good off the shelf immediately implementable strategy for learning a classifier, okay, on many problems, and that's why it's quite popular, and that's the reason why this is the only classifier ensemble that we are considering in this course. Okay. Having said that, let us go back and look at AdaBoost a little more closely. All that we have done so far is giving you an algorithm which looks like a black box. Why those kind of weight updates? Why that particular alpha m should be the weight in the final classifier? Okay, nothing is clear. I mean, as a matter of fact, it looks like black magic because you don't even know where we pulled out all those expressions from. So, what we will do for the rest of this class is we look at AdaBoost from what is called from our standard risk minimization viewpoint. Right. So, we have been looking at all our classifiers as essentially you choose a appropriate loss function, and then you pose your classifier learning problem as finding a classifier with minimum risk. Of course, I can't calculate risk. So, we do empirical risk minimization. All our classification algorithms are essentially empirical risk minimization methods, except that we choose different loss functions, right. So, the same thing we did in SVM case. First, we present SVM as an interesting optimization problem, then show that it also has a risk minimization view. Okay. So, like that we will now show that AdaBoost has an interesting risk minimization view. The loss function that is appropriate for AdaBoost is what is called an exponential loss function. That is what AdaBoost minimizes. So, we will first briefly define exponential loss. and the set of classifiers or the hypothesis space over which this algorithm searches is not individual classifiers, but ensemble classifiers. So, we have to introduce a proper model class for this. So, we will introduce a class of models that are called additive models, which exactly capture the ensemble classifiers. Then we show that AdaBoost is essentially finding an additive model by minimizing empirical risk with respect to exponential loss function. So, if you think that we are using exponential loss function and want to minimize empirical risk while searching over this class of additive models, the resulting algorithm looks like AdaBoost. To be more precise, it is not a full minimization to find a global minimum, but let us say a minimizer which uses a greedy heuristic. I will tell you shortly what a greedy heuristic means, but a slightly approximate way of minimizing empirical risk on the class of additive models is what AdaBoost is. Okay. That is another way of looking at why AdaBoost gives good performance. Okay. So, first let us look at the exponential loss function. Exponential loss function simply L of hx comma y is exponential minus y into hx. We have seen that many loss functions can be written as functions of y hx, right. So, if y hx is negative, the say 0 1 loss function simply says if y hx is negative, that is y and hx are opposite sign, then the loss is 1. If they are positive, the loss is 0, right. That is of course a non-convex step function. Then we have seen the hinge loss of SVM, which tries to give a convex approximation to this. We also saw that the square loss is another convex approximation to the 0 1 loss function. So, similarly exponential also is an approximation in the following sense. If you think of x and y, hx and y both are plus 1 minus 1, then it is very easy to see that whenever they are of the same sign, the loss will be exponential minus 1, and whenever they are of opposite sign, loss is exponential plus 1. So, there is a lot of difference. So, essentially the loss is low if y and hx are the same sign, high otherwise, and of course, the same conclusion holds even if hx for example takes real values, because it will only so as long as y and hx are the same sign, it will be exponential minus something. Whenever y and hx have opposite sign, exponential plus something. So, between correct and incorrect classification, there is a lot of difference, and in that sense it is essentially like a 0 1 loss function, but unlike 0 1 loss function, it gives me a convex loss function. Okay. It is a convex function of y hx. So, this is it is one more convex approximation to the 0 1 loss function. That is of course a good enough reason to consider exponential loss, but we can still ask, is this we have already so many loss functions, why one more loss function? Because exponential loss has many interesting properties. I will just state one. It can be shown that if I am minimizing risk under exponential loss or all real valued functions such, not just binary valued functions such as we are considering here, but if you minimize risk or all real valued functions h, then the minimizer is half log of odds, right. So, y is equal to 1 given x is posterior probability of class 1, y is equal to minus 1 given x is posterior probability of class minus 1. So, this is essentially in a 2 class case, this is odds for class 1. So, if the posterior probability of class 1 is greater than posterior probability of class minus 1, then this factor will be greater than 1 and log will be positive. On the other hand, if the posterior probability of class 1 is less than posterior probability of class minus 1, then the factor will be less than 1 and log will be negative, right. So, essentially if I use sign of h star x, I get the optimal classifier, right. So, if I can find h star, which is the minimizer of risk and exponential loss, and use its sign, that will give me the base optimal classifier, right. Of course, this is over all real valued functions, but that notwithstanding, this is a very interesting reason why one should look at exponential loss. This is, as a matter of fact, one of the reasons for which because of which exponential loss function is attractive and used in many pattern recognition applications. So, with this we will take that we want to use exponential loss, right. So, let us look at what are, so this is the loss function that AdaBoost uses, and let us look at the model class. As I said, model class is additive models. So, this is the kind of classifiers we want to consider. Fm of x, f subscript m of x is sign of some summation m is equal to 1 to m beta m hm x, where each hm is a classifier and each beta m is some real number, right. Now, we take sign essentially because we are considering two classifiers here. Because we are considering two classifiers, we take the sum of all the classifiers and take its sign for our final classifier. But in general, I do not have to take the sign. So, any FM that can be expressed as sum of classifiers like this is essentially a ensemble classifier. So, in general, FM is a weighted sum of the outputs of HM. Of course, FM need not have to be classified, it could be a regressor, so it could be just a function model. So, in general, any FM that is a weighted sum of outputs of so many HM is called an additive model. So, an additive model is simply addition of many other simple models. Okay. So, if each HM is some function, some regression function or classifier, then summation m is equal to 1 to m beta m hm, right. So, this is what an additive model is about. Okay. So, the class of additive models are simply obtained as weighted sums of ordinary base classifiers or ordinary functions. Okay. Let us say if we are learning an ensemble, we are essentially learning an additive model. As we already know, this is the kind of this is an ensemble classifier. If each of the HMs is a classifier, this is like a weighted majority. We have to somehow combine HMs. So, this is one way of combining. So, we can think of classifier ensembles as essentially learning additive models. So, let us say we want to learn an additive model, that means a model of this form. Let us assume m is fixed. So, the model of this form, any specific member of this model class is specified by specific values for beta m and hm for m is equal to 1 to m. Right. So, that is what I have to learn actually. So, let us say we want to learn an additive model by doing empirical disk minimization. What is empirical disk? Summation I is equal to 1 to n L of your model, say f of xi, fm of xi, comma yi. Right. So, that 1 by n does not really matter in the empirical disk. So, drop that 1 by n. So, I is equal to 1 to n L of what is my model? M is equal to 1 to m beta m hm xi, comma yi. Right. This is my, if L is the loss function, then this is the loss on xi yi, because this the first term here is the value of a model specified by beta m and hm on xi. This is yi. Right. So, this is my loss. If I sum mod I is equal to 1 to n, that is my empirical loss. So, essentially, if I want to do empirical disk minimization, I have to minimize this expression over beta m and hm. Right. That is what empirical disk minimization would be. In our particular case, L is a L hx comma y is exponential minus y hx. So, it will be exponential minus yi into the sum. Okay. That will be the empirical risk with respect to exponential loss, and that is what we want to minimize. Okay. Of course, this minimization is over beta m hm, m is equal to 1 to capital M, right. We have to learn all of them. We have to learn beta 1, beta 2, beta m, h1, h2, hm. So, we have to simultaneously optimize over beta 1 to beta m, h1 to hm. What do you mean by optimize over h1 to hm? That means, for each hm we are searching over a class of base classifiers, maybe there will be some parameters, parameter is a family of base classifiers. So, those parameter vectors is what we have to learn. So, we have to optimize over so many parameters at a time. This is a really hard optimization problem. But whenever you have this kind of additive models, one standard heuristic is what is called a greedy approach. I want m classifiers. So, really I am asking which particular set of 100 classifiers is best. Instead of doing that, what I can say is, suppose I want to use only one. What is the best classifier? I take that. Now, if I want to use two classifiers, I am saying only given that this is the first classifier I am using, what is the best second classifier? Because that may not always be the best. If I am using the only one classifier, what is best may not be even a member when I want to use 2 or 3 classifier ensemble. But this is called a greedy approach, because I accumulate one by one. So, at each stage we optimize for putting one more classifier in a model. So, if I have already learned m classifiers, when I am learning say first classifier, I act as if I only want one classifier. Having learned that one classifier, now I want to add one more. While adding one more, I cannot change what I have already learned. That is the characteristic of greedy approach. Okay. So, at each stage we optimize on one more classifier to be added to the model without changing anything that we have already learned. This is called a stage wise learning of additive models. Okay. So, of course, I would still be minimizing risk with respect to the entire model, because I am adding one more to the model. So, that is the model I consider, but while optimizing over that model, I am only optimizing over the new element, new component I am adding to the model. That is what the greedy approach means. AdaBoost is essentially doing empirical risk minimization with respect to exponential loss for stage wise learning of an additive model. So, it is not learning the optimal additive model, but doing the greedy approximation to the optimum. So, this is the model class, right? We have to learn. So, let us say as a notation, this capital M can be variable. So, for any little m, fmx is sum of this from j is equal to 1 to mx, which also means fmx is f1 minus 1x plus beta f hmx. That is what is meant by stage wise. So, at stage m, I have already learnt the m minus 1 stage classifier, and now I want to add one more stage to the classifier. So, this is the new model I consider. I am asking what is the best new model for me, but when I say best, I can only tweak beta m h. Okay. So, at stage m, we have already learnt m minus 1 component classifiers and are trying to add one more. Okay. So, we need to find the best beta m and hm to minimize the empirical risk of the m component additive model. Okay. That is the whole idea of the approach. In the greedy approach, we leave all the previously learnt ones unchanged. As I said, we are asking what is the best fm at the mth stage. When I say best fm, I minimize empirical risk by taking fm minus 1x plus beta m hmx as my model. But in this model, the only thing that is tweakable is beta m hm. I will not tweak fm minus 1. fm minus 1 I consider fixed. That is the whole idea of the greedy approach. So, in the greedy approach, we leave all the previously learned classifiers unchanged. Hence, the solution for the next component of the model is, see, this is my model and I am using my exponential loss. So, my empirical risk is sum over the examples as equal to 1 to n exponential minus yi into my model. My model is fm minus 1 xi plus beta h xi. Beta h is what I want to add at the mth stage, beta into h, and I am minimizing it over all possible beta and h. This is my empirical loss, empirical risk under the exponential loss. So, if I have if I decide to use the beta and h as the parameters of the next component I am adding to my model, then this is the empirical risk I get. So, I am minimizing it over all beta and h, and that minimizer is what I am calling beta m and hm. That is what I am going to add at the mth component in my model. Okay. So, let us define WIM is exponential minus yi into f m minus 1 x. Why do I want to do that? See, if I look at just the empirical risk expression, I have exponential minus yi m minus 1 xi into exponential minus yi beta h xi. Exponential minus yi m minus 1 xi does not change by changing beta and h. So, it is outside this optimization, right. So, that is why we can take that factor out. So, WIM is exponential minus yi m minus 1 xi. We can think of WIM essentially as the weight for xi at stage m. These are the, we will ultimately show that these are the weights that AdaBoost is actually using. Since this depends only on fm minus 1, right, it is a constant for the optimization problem at the mth stage. It does not affect the optimization problem at the mth stage. So, now I can write the optimization problem effectively as minimize over beta and h I is equal to 1 to n WIM exponential minus yi beta h xi. So, I find the beta h that minimizes this, and those ones is what I call beta m hm. That is what argmin means. So, that will be the solution for my mth stage component classifier. So, this is what I have to do. If I am doing stage wise empirical risk minimization, using exponential loss, right. Then at the mth stage, I want to add mth component. Mth component in our model is represented as beta m into HMX, beta m into HM. So, my empirical risk for the model will be some unspecified weight at this point, because that depends on the Fm minus 1 part of the model, into exponential minus yi beta hxi, and which is summed over is equal to 1 to n to get me the empirical risk, and this is minimized over beta and h. Okay. The minimizing beta and h happen to be my mth component. Okay. What we are first going to show is that if I minimize this expression over only h by keeping beta fixed, right. For any fixed beta, I want to minimize it over all possible classifiers h. Then the h that minimizes this is the h that minimizes this, I is equal to 1 to n wim indicator y not equal to hxi. This is nothing but the weighted error. See, if you look at I is equal to 1 to n wim indicator y not equal to hxi, this is the weighted error of a classifier h, weighted according to these wims. And we are saying my hm is the classifier that has the least weighted error, right. If these WIM happen to be the same weights that we use in AdaBoost, then this is exactly what AdaBoost is doing, right. HM is essentially the one that has the least weighted error, and this is the error that we have considered in the AdaBoost algorithm. Of course, we have not yet shown that this WIM, which we defined with respect to Fm minus 1, has anything to do with our weights, but we will show that later. So, essentially we will first show that if I am minimizing this is my mth stage optimization problem for stage wise learning of additive models. So, if I did this optimization over only h for fixed beta, no matter what value of fixed beta, as long as beta is positive, this will be the solution. That is very interesting, because that is exactly what the solution AdaBoost is also looking for, because for any given classifier AdaBoost calculates this as the error, and we are looking for classifiers with low errors. So, essentially AdaBoost is at the mth iteration, AdaBoost is choosing HM that has least value for this. May not be doing this optimization fully, but that is what it is picking. Okay. Let us show this. To show this, let us first remember that because both y and hxi are minus 1 plus 1, that is only the binary two class case is what we are considering. Because of that, the product is also binary, because both individual each y and hxi are minus 1 plus 1, yi into hxi is also minus 1 plus 1. Now, this is what I want to optimize. So, inside the exponent I have yi hxi, forget the beta. So, the yi hxi factor takes only minus 1 plus 1 values. This means for each I, this exponential factor is a constant, does not depend on I mean depends on I, but it can only take one of two values. On each I, it is either exponential minus beta or exponential plus beta. So, this expression can be either e power beta or e power minus beta, because yi into hxi is always minus 1 plus 1. We use that to rewrite this expression. Okay. Let us say A is the expression that is being optimized, that is A is this summation. See, we are optimizing, we said we are optimizing this only over h now, keeping beta fixed. Let us call this expression some A. So, A is this expression, I is equal to 1 to m wim exponential minus. Now, we know that if yi is not equal to hxi, this y and hxi will be minus 1. So, this factor will be exponential beta. If yi is equal to hxi, this factor will be exponential minus beta. So, I can write this as sum over I wim into indicator y not equal to hxi. So, this will take wim for only those I for which yi is not equal to hxi, otherwise this will be 0. So, for all of them it will be e power beta, plus it will be e power minus beta for all I such that wi is equal to hxi. So, I can write this summation now like this. Now, I can further manipulate this. Indicator yi is equal to hxi is same as 1 minus indicator yi not equal to hxi. Indicator y equal to hxi is 1 when y equal to hxi. If y equal to hxi, y equal to indicator y not equal to hxi will be 0 and vice versa. So, this indicator is nothing but 1 minus this. Now, I can combine this term with this negative term here to get e power beta minus e power minus beta of WIM indicator y not equal to hxi, and what is left is the constant term e power minus beta WIM. This of course does not depend on h. So, minimizing h, I only need to minimize over this. Even here, as long as beta is positive, e power beta minus e power minus beta is a positive quantity. So, it does not affect my minimizing. So, minimizing this whole expression over h is same as minimizing only this expression over h. That is the result we are looking for, right. The second term in the above expression is constant, hence for a fixed beta greater than 0, optimizing the above over h gives us hm is equal to arg min h is equal to 1 to n WIM y, right. That is this term. This is what we wanted to show. This is interesting, as we already said. The next classifier that we should add is the one which minimizes the weighted misclassification error. So, the weighted misclassification error that AdaBoost is looking at is very important. Of course, provided this WIM turns out to be the weights there, that we will see at the end. So, this is the error of the classifier that we are finding in each iteration AdaBoost also. So, we note of course, that we have not yet shown that WIM would be the same weights as in AdaBoost algorithm. We will do that before the class is over. But let us complete our minimization of empirical risk. To minimize empirical risk, we have to find HM as well as beta, which we first showed that no matter what the beta value is, as long as positive, and we can have only positive weights. So, for any positive beta, we know how to find HM. Now that we have found HM, with this HM, we have to find the best beta, that will be my beta m. Okay. So, with the given HM, we need to find beta m to optimize over beta. So, what do I have to optimize? So, we already seen this is what we are being optimized originally, and that is same as this. Now, I know this term is optimized by h is equal to hm. So, I will put hm there. So, now putting hm there, I have to optimize this whole thing with respect to beta. Optimize meaning minimize with this whole thing with respect to beta. So, to find beta m by optimizing over beta, minimizing over beta, this term. Okay. So, to make it simpler, let us remember that because summation over I WIM will be a constant. See, WIMs are exponential something, we defined it to be exponential by f of m minus 1 xi. So, the exponential something is always positive. So, these weights are all positive. So, sum of weights will be positive. So, if I just multiply this entire objective function by a positive constant, it does not change the. So, the optimization problem will be same if we divide it by this. If we divide it, we get here summation over I WIM I of indicator y not equal to hm xi whole divided by summation I y WIM, we will give some name to it, we will call it JIM. Summation over I WIM indicator y not equal to hm xi whole divided by summation over I WIM. On this term, this will go away, I will get only e power minus beta. So, this factor which does not depend on beta, we give some name JIM. So, now what we need to minimize over beta is e power beta minus e power minus beta JIM plus e power minus beta. This is minimizing this over beta is what gives me beta m. Now, this is very simple function of beta. Let us differentiate and equate to 0. If I differentiate equal to 0, I get e power beta plus e power minus beta into JIM minus e power minus beta is equal to 0. You solve for beta. So, that gives you the optimal beta m as half ln 1 minus JIM by JIM. I hope all of you still remember ln 1 minus JIM by JIM from the AdaBoost algorithm, that is alpha m. That is the vote that mth classifier has in the final classifier ensemble. In our model, beta m is the vote that the mth classifier has the final ensemble. This beta m happens to be just half of alpha m. So, this is our final solution. At the mth stage component beta m hm that we want to add. Basically, my final classifier is sine of beta 1 h1 plus beta 2 h2 plus beta 3 h3 so on. So, having learned up to m minus 1, I am learning mth one. At the mth stage, the best hm is one that minimizes the weighted error. Beta m is half of ln 1 minus JIM by JIM, where JIM is given by this. Okay. This exactly corresponds to AdaBoost algorithm. Let us see one by one why. We are trying to find hm to minimize the weighted error, right. That is exactly what AdaBoost also does. Then we are always keeping WIM normalized. So, summation I WIM is 1. So, JIM is same as summation over I WIM indicator y not equal to hxi. So, that is exactly the xim that we defined in the algorithm. With respect to the xim we defined in the algorithm, in AdaBoost, the alpha m is ln 1 minus xim by xim, whereas for us the beta is twice alpha m. So, alpha m is the final vote in the weight of the vote, beta is the weight of vote in my model, but essentially because I am taking sign, whether I put 2 beta m or whether I put beta m alpha m, it only changes a little bit. So, but any case in the final thing, what AdaBoost is putting alpha m, here we are putting 2 beta. Okay. Now, to complete analysis now, so what we are showing is that essentially what we learn is what AdaBoost algorithm is doing. So, if we are essentially doing empirical risk minimization using exponential loss function, the factors we get are same as what we get in AdaBoost if this Wi is same as the way weight behaves in the AdaBoost. So, to complete our analysis, we have to show that the WIM are actually the weights used in the algorithm there. Specifically, what do you have to show? Because anyway, at the first stage, F0 is arbitrary. So, we can, and because we want to keep weights normalized, it will be 1 by n. So, we only have to show that WIM plus 1 to WIM algorithm is what I get. Okay. This is what we do next. Recall our notation, Fm is j is equal to 1 to m beta j hj, this additive model up to little m. So, which means Fmx is Fm minus 1x plus beta m hmx. Okay. Remembering this, we know Wim is exponential minus ya into Fm minus 1x. This is how we define Wim in our empirical risk minimization. Right. So, Wim plus 1 will be exponential minus yi into Fm xi. Okay. Now, we know Fm is this. So, I substitute that, it will become minus yi Fm minus 1 xi minus yi beta m hm xi. Now, the first factor is what Wim is. So, this is Wim into exponential minus yi beta m hm xi. So, under our definition, Wim plus 1 is Wim into this. Of course, even in the AdaBoost, these next weights are obtained by multiplying the current weights with the exponential factor. So, to just show that this is the right exponential factor. As we know, because ultimately we are normalizing these W's, a constant does not make any difference. Okay. So, let us see how this factor is same as what we put in the algorithm. So, the factor we have is exponential minus yi beta m hm xi. Okay. Since yi hm xi belong to plus 1 minus 1, right, we can write yi hm xi as 2 times indicator yi not equal to hm xi minus 1. Why? Suppose yi and hm xi are of opposite sign, then this indicator will be 1. So, this will be 2 minus 1 will be 1. On this side, they are opposite sign. So, minus yi hm xi will be plus 1. Conversely, if yi and hmx are of the same sign, then this indicator will be 0, so it will be minus 1, and this side also it is minus 1 because y and hm are of the same sign. So, I can always write minus yi hmx as this. Now, I have minus yi hmx here, is beta m into minus yi hmx. So, I can substitute minus yi hmx there. So, that gives me Wim plus 1 is Wim into exponential, what do I have? yi hmxi is 2 into indicator minus 1. So, 2 beta m indicator yi not equal to hmxi, beta m is already there, right, yi hmxi into beta m, that is where the beta m comes from. So, the exponential, there will not be any minus because this minus yi hmxi is what is given by this. So, 2 beta m indicator of this into this minus 1 will simply give me exponential minus beta m. Right. Now, the 2 beta m is exactly equal to alpha m. So, this is Wim plus 1 is Wim exponential alpha m I y not equal to hmxi into some exponential minus beta m. In the AdaBoost case, we first do w I prime m plus 1 is w I m into exponential 2 beta m, which is same as alpha m into indicator y not equal to h of x I, and then normalize it. Because I am normalizing, if I am multiplying all weights with a constant that does not depend on I, that will go take away normalization. So, this weight update, right, is exactly same as the weight update that is used in AdaBoost, because 2 beta m is same as alpha m, that WM are always normalized. Okay. So, so let's go back to as you seen, if I do stage wise minimization of empirical risk under exponential loss, this is my m stage solution. You find HM that minimizes the weighted misclassification rate, right. Calculate the misclassification rate. If WMs are normalized, then this is simply JM is summation WIM this, and then the weight itself is given by this, right. This is exactly what the algorithm is doing, as long as WIMs are normalized weights, right, and that is what we have shown now. WIM exponential alpha m to I y not equal to h m x I into some constant. This constant does not matter because I am normalizing it. So, know the 2 beta m is same as alpha m and the WM are always normalized, hence the weight update is to be AdaBoost. So, what we have shown is essentially the AdaBoost algorithm is finding a minimizer of empirical risk, not a true minimizer, but an approximate minimizer using a greedy approach, right, under exponential loss function. Thus, AdaBoost can be understood as learning an additive model in a greedy fashion by minimizing empirical risk under exponential loss. So, this is one way in which I can assume AdaBoost successful in practice. AdaBoost, as I mentioned earlier, is fairly successful, even very simple, almost simple minded classification algorithms. If I take enough of them, learn through AdaBoost, learn through this proper weighting, gives very good classifiers. Okay. As a matter of fact, for AdaBoost to work well, it is often more convenient if the component classifiers are a little less accurate. In the sense, if I am using very high complexity component classifiers, one classifier may have very high accuracy and it may dominate everything, right. So, it is often better not to do that. All kinds of things have been used, including neural networks and decision trees and so on. And today there are many other variants of this boosting algorithm, and as a matter of fact, more theoretical is also available in terms of information theory and so on as to why this boosting occurs. Boosting is one very major new area in pattern recognition. New meaning in the last 10-15 years is a great idea to come up into pattern recognition. So, there are many more new results in boosting. But no, this is a interactive course, so we just consider one basic boosting algorithm, but this is one that is most often used and very useful in practice. Okay. So, this brings us to the close of the course. We have completed all our lectures. So, I will just briefly review back what all we have done. We started with the basic idea of pattern recognition, feature extraction and classification, a two-step model. We have seen that learning functions in general has the same flavor. So, when I am learning any model f, the basic problem is you give me examples x I, y I is equal to 1 to n, and I have to learn some model f such that f of x I is a good approximation to y I, not just in the training set, but any future things that I may get. Now, we like this problem in general, look many examples, and then decided that we look at it only in the statistical sense. This entire course is only about statistical pattern recognition. So, we looked at statistical decision theory, we looked at Bayesian decision making. So, we defined loss function, risk, what is the optimal Bayes classifier, and shown that essentially if I can calculate posterior probabilities of classes, then I can implement a optimal classifier. Optimal in the sense minimizing misclassification rate or any other kind of a cost for misclassification. We have also seen that minimizing misclassification may not be the only criterion. There are other criteria such as Neyman Pearson, where we want to keep one kind of error always low. We have seen how that such classifiers can be derived. Then we spent some time asking, if this is how we want to implement statistical pattern recognition, how can we implement them? So, we need to calculate posterior probabilities, which means we need class conditional densities and prior probabilities, and we have spent time in asking how we can estimate them. So, we considered both parametric and non-parametric ways of estimating. In the parametric method, we looked at both maximum likelihood and Bayesian estimation. We looked at nearest neighbor and kernel density estimates and non-parametric estimates. And then we also looked at mixture densities. These are all for single densities, but we also looked at mixture densities and the ML estimate using EM algorithm. Right. So, one method of implementing classifiers would be through density estimation. Then we looked at other methods. Then we looked at discriminant functions, linear discriminant functions. We looked at perceptron. We looked at Adeline, which is a linear regression learning algorithm. We in general looked at least squares method of learning linear models, both for classification and regression. Looked at the relationship between least squares and as a Bayesian or ML estimate under some assumed model. We looked at regularization, why regularization needed, why model complexity is an issue. We looked at from the classical perceptron algorithm all the way to logistic regression and special linear discriminant. Then we stepped back and looked at statistical learning theory. We developed the theme of risk minimization a little more and showed why empirical risk minimization is useful, when it will work, when it will not work, what is the complexity of model class. We characterize the complexity of model class using VC dimension. Okay, we explained what VC dimension is and essentially justified empirical risk minimization. Then we moved on to looking at nonlinear classifiers. We only considered two classes of nonlinear classifiers, one based on neural networks, both feed-forward networks with sigmoidal activation as well as radial basis function networks, and then we looked at SVMs. Unfortunately, due to lack of time, we did not consider one other very important topic. That is among the first level topics that should be covered in a basic pattern recognition course. One topic that is not covered in this course is decision trees. Right? That is a very good class of classifiers, but for lack of time, we did not cover the decision trees. But we covered the other two major class of nonlinear classifiers, neural networks and SVMs. In SVMs, we also looked at kernel based methods, which are now the most popular pattern recognition methods, and a lot of theories there around them. After that, we looked at model assessment, model estimation, bias variance trade off. We looked at how to estimate the final error of the model, how to choose model parameters. We looked at cross validation. We looked at bootstrapping. Arising out of that, we finally ended the course by looking at classifier ensembles, bagging and boosting, and AdaBoost. Okay. I hope you people benefit out of this course. Thank you very much.